Hello. Okay. So, hello everybody. So, great to see quite a few people around here. I was somehow expecting most of you guys are already on the way back, so it's quite good to see. I will talk to you a little bit about 15.4, so 802.15.4, the wireless protocol, and also about 6LoWPAN, which is an adaptation layer, and how you can add that to your embedded Linux device. So, let's get started. So, I start with a little bit of motivation here. Then I will go into the details of the Linux WPAN project. This is basically all the software behind that, which is kernel side and user space side. Then I will have a look at the hardware that's currently supported by our project and other parts that are not supported. I go a little bit into the hardware configuration. Luckily, these chips are really simple to connect to your hardware, so that's not too difficult. And then I will look into the configuration, so what you need to do to bring it all up and make it working for you. And then I look a little bit into the communication with other operating systems, in this case more for the, let's call it IoT space here. So for example, Riot and Contiki, which are really devices for microcontroller. And yeah, that's something we really need to communicate with here. Okay, motivation. So 15.4. The specification is from IEEE. It was defined as for low-rate wireless personal area networks. By now, they completely skipped the personal area part of it, which makes a lot of sense because it's not really used for that much. It's not only low rate, but it's also for low power. So if you have a configuration with an MCU, so not a full Linux system, but if you run something like a Riot or Contiki on it, and you have an MCU with a transceiver, you can have times where like maybe months, maybe even a year with the correct duty cycle on a normal battery. So that's quite good compared to something like Wi-Fi, for example. Obviously, there are some downsides of that. So the MTU that this network is using is like only 127 bytes. Which is quite challenging, especially for if you want to run IP version 6 over it, but I come to that later. And the bandwidth is also not that fast, but normally it's okay because you're normally just doing types of machine-to-machine communication. You're not going to stream HD videos over YouTube or something like that, so that's okay. Sometimes this is confused with ZigBee. That is because ZigBee uses the same PHY and MAC layer from 802.15.4. So they put other things on top of that for the routing and addressing and so on. So that's kind of a, confused thing sometimes. So 6LoWPAN, basis on top of these IEEE standard. 6LoWPAN itself is specified by the IETF. So the guys who brought us the most of the protocols we're using in the internet today. They started 2003 with the specifications there, and then it's still ongoing. So the main things are done, but there are always smaller items they are going to specify. And as you can see there on the green part, 6LoWPAN itself is really just an adaptation layer sitting on top of the NAC, but below the IP layer. So that's not really fitting into the ISO model, but that's really just making sure that the adaptation is there. So why you want to have this kind of 6LoWPAN adaptation? I mean, people want to use IP version 6 over this kind of networks, which is a bit scary when you first start thinking about it, because, an IP version 6 packet is 128 byte, or could be, and then you have the MTU on the other side of just 127 bytes. So that really also breaks down to having a real problem with the headers that are normally in place if you want to transmit over this wireless links. So there's a bit of a worst case calculation. You start off with 127 bytes, and then you have the maximum frame header itself. So if you go for an extended address and you have all kind of options enabled, then you're already down to 102 bytes. Then you want to have link layer security enabled to make sure that even on that layer there's nobody eavesdropping on you. So you want the strongest encryption there and the strongest authentication. So you're, again, 20 bytes down, so you're down to 81. And then you have the normal IP version 6 header. You would use that. That is, again, 40 byte, and then you would even use something like UDP. And then you have like 33 bytes for payload. And that is that's where the whole package. That's like 25% you can get out of this one package. So that's really, really bad. So what is the solution here? So the ITF got ahead and specified the 6LoWPAN adaptation layer to make sure that it's going to reuse a lot of the stuff that's already present in layer 2. And you can use that in layer 3 and IPv6 in that case. And they also start to elite a lot of things that are normally present in the header but are not used in this kind of network, so that's helping a lot. So in a really good situation where you just do linked local communication, you could go down to a header size of just 6 bytes compared to the 48 bytes you normally would have with IPv6 and UDP. The ratio is a lot better there in that case. Yeah, and you can see all the details here. So you still would have the frame header, obviously, and the security header, but the 6 bytes, is that what you condensed really the IPv6 stuff here. You can even go down and if you know that all the application layer protocols you are using are really doing checksumming and everything, and you're really sure that that is all fine, you can even elite that one. It's not recommended, so that's not what we are doing by default, but it could be done. So why would we do that on Linux? Because most of the people I talk with say that they only would use that on microcontroller boards and really small things. But on the other hand, you need some kind of gateway or something like that that actually connects these kind of nodes to the wider internet or to your local network or something like that. And that is really where Linux comes into play. I mean, there are all these platforms that are already running Linux, or access points and all the other small plastic boxes in your home already have support for that. So the idea is to really have full support for that in the mainline kernel, and then you can really just add a bit of hardware support on the transceivers, and then you can mostly run it out of the box. Some examples there's the Google OnHub access point. They already have a 15.4 transceiver hardware inside this thing, but it's not enabled just yet. I mean, they have support for, they have plans for that as far as I understand it, but they don't have it enabled. And then there's the CI40 board from Imagination Technologies, which is kind of aimed to be an IoT hub in the home. That one also has a 6LoWPAN 15.4 transceiver directly on the board. And then there's also the, I just yesterday learned there's the BeagleBone Air, which is a kind of strange version of the BeagleBone from a Korean company, and they added 15.4 transceiver and some other bits as well. Better that way? I can try. Binary search here. Better? Okay. Okay, so the project itself, I mean, it was already in 2008, some people at Siemens started these. At the point they called it Linux Zigbee, which is kind of confusing for a lot of people. In 2012, the mainline effort started for that, so, and by now we are doing all the work directly into the mainline kernel. And we also renamed the project to make it a bit more clear that we are not related to Zigbee here. It's a bit of a problem because the Zigbee Alliance, the specification that's available there, you're not able to combine that with the GPL of the kernel easily. I mean, you can do some parts in the kernel and do the rest in user space. You might be able to do that, but we are not having any idea on any plans on supporting Zigbee. So if anybody wants to do that, they're free to do, but it's not on our agenda. And yeah, the normal kernel development model, you just post patches to the main list, discuss things there, and then they're getting applied. It's a really small community, so there are only like 2 core developers, and I'm one of them, but I'm really only spending like 10 or maybe 15% of my time on that. And the other one is still a student, so right now he has a lot of time to work on that. Not right now, but he had a lot of time, and maybe we'll see when he's going to get a job how much time he will have left for that. Then we have a few more people that are actually working mostly on the driver space, so to support their own hardware. We have almost 100 people on the main list, so there is quite some interest. And we have normally like 33 people around on IRC. So there's interest in using it, but not that many people that are actually working on it. Yeah, so the support we have right now is we have a variety of drivers for the different transceivers that are out there. Most of them are soft Mac drivers, so that we are doing the whole Mac Mac software stack in the kernel itself, so not on the hardware. There are hardware Mac transceivers as well. We support one of them, or one is in the process of being supported, and we really need to do a lot more work there to get more of these devices into the kernel. We have full support for fragmentation and reassembly for 6LoWPAN. That's in the old RFC that actually started that, and then we have support for the IP header compression and the next header compression for UDP. So that have been the examples I've shown before. That's in a newer RFC from there. And the same stuff is actually also used by Bluetooth, by the Bluetooth subsystem, because there's also a 6LoWPAN over Bluetooth specification from the IETF, and there's a lot of other link layers that are either already specified or in the process of using 6LoWPAN on top of their link layer. So there's work ongoing for DAC, there's work ongoing for MSTP, and some power line communication things and so on. So that's really a lot of things. But only Bluetooth and 15.4 are the things that are supported in the Linux kernel, so that's the only things we are doing there. We have support for link layer security, which is working but hard to use from the user space perspective, because there's no in the spec there's no specification how you do rollover of keys, key handling, and all the other things. So what is there is the basic plumbing to get the keys into either the hardware or just do it in the kernel, on the kernel side, and encrypt the frames and decrypt them, but all the handling on top of that is really not there. So that's kind of problematic. Yeah, there's testing against other Linux instances, and we're testing against Riot and Contiki. It's a really active project in terms that we are changing things every kernel release. So if you want to try it out, really aim for a new kernel. I know that's sometimes difficult on embedded boards, so 4.1 is something we can actually live at. With everything before might be problematic. So yeah, the current kind of development boards we are working with right now, there's the CI40, I mentioned that. From Emerging Technologies, that's on the right side down here. The driver for that is in the process of being merged. It's not in there yet. The most commonly used hardware platform is the Raspberry Pi together with an Open Labs shield. So that's just this small black thing sitting on top of that. So that thing is just the transceiver with a little bit of extra hardware you need there. So that would be basically what you could add to your own board. What I do, for example, is that I have various Raspberry Pi sitting on my desk, and then I have the different transceivers just wired up to the Raspberry Pi, because you only need SPI and some other GPIOs there. What you need, so, on your embedded hardware is support for device tree. So if you're running an out-of-tree support for your board, some BSP or something, without that, that might be a real problem. But I hope by now that all the embedded boards that are kind of supported, even by a vendor BSP or something, have support for device tree. If you want to go with USB, that's also possible. I mean, might not be the thing you're aiming for, but it's really convenient if you want to do the development on your laptop, or even just put it in a box that is completely main powered, and you don't want to have all the hassle in adding a new board to the system. So there's one USB stick over there. There are some more, but that one here is the best we are supporting right now. That's open hardware, so you have all the stuff available. The firmware is also open source, so you can even go and hack around on that one. We just did another run of these devices, so you can buy them again, because they haven't been available for like 3 years. And it was a bit of a pain. I mean, the original author who did that, they did a run of like 120 devices. And they sold out at some point, and nobody really had interest or the capacity of doing that. I mean, not the capacity of doing a new hardware run, that's okay, but doing all the billing and selling and all the other things is really complicated. So finally I found a company who gladly did that for us, so they are now selling them again. Yeah, hardware side. So what you need on your embedded board, if you want to add that, is really simple. So you need an SPI port, and you need maybe some additional GPIO pins. That's basically it. It can go down to just one extra GPIO pin for an interrupt handler, for example, to just make sure that you're now, when there's a packet coming in. It could be more, depending really on the hardware and what you want to do with that. There's an example on the next slide. And then you can choose between completely ready-made modules that are available. You can just hook that up, or you can completely integrate it in your own design if you want to have it directly on the PCB or whatever. So then you can mostly go with the reference from the hardware manufacturer and then go with that. Oh yeah, I mentioned that before. You can go with USB, maybe even only for prototyping or something. That helps, but in the end product, that might not be what you want to do. Okay. Yeah, so I mentioned that device tree bindings, so all the drivers we have device tree bindings. The example over there, I don't know if you can read that. So it's really basic. I mean, you can see there that's just a compatible matching over there. So that would be for an Atmel transceiver. Just the SPI speed, the clock speed. And then you have the SPI port. That would be 0 in that point, so the register. And then you have one GPIO being for the interrupt handling. And here you have some more GPIOs for this transceiver, for example. So you have a pin to actually reset the hardware, and one for the sleep state. I don't know how much we are using that, but that really depends on the different transceiver hardware that's available. So as you can see, that you can really easily add that to your existing hardware designs. So the transceivers we support, or the drivers we have right now, a lot for the Atmel transceivers. We have one for microchip as well. We have one for analog devices. We have one for TI, and the AT-USB, that's the USB dongle. So it's actually an Atmel transceiver on the thing, but there's a different communication because it goes over USB, and we have firmware support. There's the panning driver for the Cascoda. That's the chip that's on the CI40 boards. That's ongoing. Hopefully we are getting that in within the next weeks or something. Then there's these XV devices, which are kind of problematic to support because, I mean, on the one side they are hard Mac, so they're doing a lot of stuff inside the firmware of the chip itself. And one way to communicate with them is over AT commands, which is really ugly. I mean, if you want to do a drive, I mean, from the user space, that's fine. That's really nice. You can just have a serial interface and do it all in user space. You're good with that. But if you want to integrate that inside the kernel with the Mac layer there, that's a bit tricky. But there's also versions which have some kind of library API. And there's a driver out there. I never tested it. I think it's a bit rotted by now, but it could be revived. So if there would be interest in that, could be done, I guess. Yeah, so the USB thing I mentioned. Yeah, wow, that's big. So that is just an overview. I mean, the slides are uploaded, so you don't really have to go through all of that. You can just download them and have a look. I just want to give you guys an overview of what kind of stuff we are supporting and what kind of these transceivers are supporting. So this column here would be if you have a driver for that. So most of them are covered. I mean, some of the drivers obviously support more than one transceiver. That would be for the Atmel chips, for example, would be the case. And then you can see if it's on the 2.4 gigahertz band or if it's on the sub-gigahertz band, which is kind of problematic because it's not easily usable everywhere. So, but you can go with that if you want. This ARRET, that means automatic retransmission. That's a hardware feature that's quite useful because the timing, you have to send out an egg, which then would trigger a retransmission or not because it's missing. It's really tight timing, and we are not easily able to handle that in software on the Linux side. I mean, I haven't tried with preempt RT patches or something like that, so I could look into that. But the hardware normally has some extra support for that, so acceleration for that, and so you can really use that. If you don't have that, that might be a bit tricky. For example, the CC2520 from TI, they don't have that, which is completely fine on when you're running it with a real-time OS on some microcontroller or something like that, because you can just emulate that. On the Linux side, that's a bit tricky. And then on the other side, you have just the specs they are covering. There's just what versions they are supporting and what not. And for example, the 15.4G over there, that's an extension of the original specification that gives you a bigger MTU, actually. So that there are specifications in that regard as well. We are not really supporting that well right now. So that's mostly because we don't have the hardware around to test it, actually. If you just want to start a little bit and get something started, maybe then while you do the software support and the hardware guys are just ramping it up and getting it extended, you can already start with just a virtual driver just really a fake loopback driver we have there, really similar to what the hardware simulation driver is from the wireless group. It's really great for testing. You don't have to have all the devices around. And you can also do some tricks with it, like having Riot or OpenSweat as a completely additional stack running on top of this virtual driver. So that means that the whole Mac stack from these different operating systems can really run on the loopback driver. So it's really nice for testing and so on, not really that much for production. Yeah, so you can see you just load the fake LB module there, and then you just add the number of devices as an option, and then you're normally done. So once you have these hardware added to your device, you really want to start, you need to configure it at some point and really make sure that you can communicate with other devices out there. So what we have there, the counterpart of the kernel support we have is the WPN tools. So that the main binary there is the IEEE tool that actually does all the configuration. That's really also quite close to the IEEE user space utility from the wireless group, so that's not too far away. The netlink code actually is also borrowed from their side. So what you do there is you can configure the PHY options you have on that transceiver, and you can configure whatever MAC layer parameters are available. The basic things you have to do to get anything working is to configure the PAN ID and the channel. I mean, PAN ID might drop that, but the channel is something you need to make sure that they are really can communicate to each other. So 15.4 does no channel hopping or anything, so really set a fixed channel, and you need to make sure that the other device is on the same channel. So if you want to have like a bit more a poor man's frequent channel hopping, you need to make sure that you have an upper layer that actually informs all the nodes that you're switching channels and stuff like that. So, but that's nothing that's in the lower levels there. Yeah, you can set a short address, you can power settings and stuff like that. So frame retries is also, I mentioned that before, how often you would retry to send a frame to a node, and if it's before you actually report an error or something like that. So. Yeah, so the packages are packaged by some distributions. Some are a little bit behind, and some don't have support for that. So if you're interested in helping with that, that would be cool. If not, compiling it from source is really easy. So the only dependency we really have is the netlink library. That's all. So once you have the basic stuff set up, you need to do some testing, or you get to see if these devices actually can talk to each other. And you normally want to do that before you start with the whole IP version 6 stack on top of it. So what you can do is we have a small utility which is kind of a ping utility on the 15.4 layer. It's not the full feature you know from your normal ping utilities, but it's a good start actually. So you need to run the daemon on one side, because that's not something we can inside the kernel, and the protocol is not specified or something, so you need to have on the other side have a daemon running. But that does nothing else but getting all the frames and then sending the same stuff back. So the real logic is inside the client here. Anyway, so you can just go and ping the other side, have different count or different sizes and stuff like that. So you can really do some early measurements as well there. So the device bring up, if everything is right with your device tree configuration and all the other things are working fine, the WPN interface shows up directly after booting. And from there you can go and see if you want to use 6LoWPAN on top of that and configure it. So if you go from up to down here, setting the interface down for LoWPAN 0 would only be the case if you configured the device before. Normally it would not, for the first boot up, it would not show up. Then you set the device down, then you use the IWPN utilities here to set the PAN ID, and then you are setting the channel as well. That would be channel 26 here. The 0 there is just a page, so at some point there have been more frequencies available for this specification, and they started to paging the different frequencies here. So that looks a bit odd there, but yeah. Normally you really just have a 0 there. It's really seldom that you have a transceiver that does something more. Yeah, and then you have this line here, which is actually the need if you want to get 6LoWPAN on top of these interface going. So that actually says that the type is LoWPAN. So and then you get a new interface called Open0, and yeah, you just set the interfaces up, and that means if you're doing any socket interaction or communication over that one, it would go plain to the 15.4 layer. And if you do anything here, that would be direct IP version 6 communication. So you really use complete normal IP sockets for version 6, and you're done. For more debugging or just to see what other devices are communicating and stuff like that, we also have support for monitoring interface with promiscuous mode. In this case, you would just delete the interface that's already there and bring it up again as the monitor type. You can see that at the end. And then you can set the channel again and bring the monitor interface up, and then you can use Wireshark, TCP dump, or whatever you want on that one. As I said, there's no channel hopping involved, so if you really want to scan around what kind of communication is going on in the place where you are at the moment, and you can change the channel in the background. So that's what I normally do. You can just keep Wireshark running, and then you're on different consoles changing the channel and see if something comes in there. Okay, so communication with other operating systems here. I need to speed up a bit here. So there's Riot. They say they're the friendly operating system for Internet of Things. They're LGPL licensed. They are actually quite friendly, so all the people we are involved with them, it's really nice we can talk to each other. We see bugs in the implementations of the other, testing it out, and so on. So that's quite good going on there. They also have testing against Linux WPAN in their release process. This is quite a nice thing. So make sure that it actually keeps working. Then there's Contiki, which is a lot older and kind of the parent of all kind of operating systems that are now in the Internet of Things space here. The problem is it's a really fragmented project, and there's a lot of forks out there, either commercial or academic or stuff like that. And it's really hard or seldomly happening that they are merging the stuff back. I mean, nonetheless, it's really still an important operating system. There's still work going on there. So that's also something we are testing against. So another famous table here. As you can see that the basic stuff that something all of us are supporting, like data and egg frames are being communicated. Something that's not supported on all of these systems is beacon and command frames. The thing is why we don't support that is that for 6LoWPAN, you don't need it at all. You need that if you want to do real management of an 15.4 network, or for stuff like Zigbee support or something like that. There's where you need beacons and command frames and stuff like that. We still plan to support that, but there's really was no priority to do that. Link layer security, that's something we support and Contiki supports, and we had some initial testing between these two as well. Riot does not support that yet. That might change at some point. And again, fragmentation and stuff like that, header compression, that's all supported by all of them. Yeah, there's Ripple, which is a routing protocol for this kind of lossy networks. On Riot and Contiki, that's directly into the operating system. On the Linux side, there's a user space daemon doing that. That's called Unstrung. There's also a kernel implementation for that, but these patches are really outdated. I need to go back and talk to the author if he's still interested in getting that into the kernel or not, but that's a completely different story. Yeah, there are other operating systems as well that support this kind of protocols. There's Mbed from ARM. I tried to look into that, but it's completely closed. I mean, Mbed OS itself, it's open source, so most of it, but the networking stack, at least the parts I'm interested in, are completely closed. So they even have the object files inside the Git repo. So there was really nothing for me to test against or check. So there's also Zephyr. They just recently switched to they started with the Contiki networking stack, but they now completely did a rewrite there. And they have actually really good support for all kind of beacons, frames, and command frames and stuff like that. So that's something I need to test against. I have some hardware at home that actually should support that. I just need to find the time to do that. And there's OpenThread from Nest Labs, which is an open source implementation of the thread protocol, which is a complete vertical stack using 15.04 6LoWPAN, but a lot of other things on top of that. So that's something we, for example, tested with the virtual drivers we had, and we tried to talk to them and find out if there's any chance that we can work together a bit more closely. But there's really not that much we have in common. I mean, it's friendly from both sides, so there's no bad blood or something, but they really want to make sure that their stuff is in one central piece and they keep it running in one in one piece and not finding good interface to act with us. So we need to figure out if there are some ways for that. A bit of a lookout here. The missing part mentions that Beacon and MacFrame support. That's something I need to work on. We need to have, after we have that, we can have coordinator support in the user space utilities and even scanning for networks and stuff like that. What we really urgently need is support for hard MAC transceivers. So that's something we really need to improve on within the next few months or something, because that really blocks a bit of hardware support, and that's annoying. Yeah, and then various other things. Different header compression techniques are still there, and then we need to find out what kind of information we need to expose to all kind of routing or meshing protocols that are using that. I mean, simple things like AQI or RSSI or something like that, that is one thing, but also like statistics, how many packets have been transmitted over this link or how many retransmit have been failed and stuff like that. So that's something we need to expose somehow. But if you are going to do an interface with user space, we really need to think carefully about that, because we need to support that until the hell freezes over on the Linux side. So that's something we really need to make sure for. Yeah, and just to sum up here, running a 15.04 wireless network on top of Linux is really easy, even right now. I mean, there are missing pieces and stuff like that, but just for getting the IP version 6 socket interface on top of these things and then communicate with some smaller sensor device and stuff like that, that's already there. That's all working. Kernel on tooling support is there. The most likely scenario it is used in right now is like a gateway or border router. You could go and have that as your small node. Even that, I mean, I know that Intel has been able to completely squeeze Linux kernel and Bluetooth user space utilities and everything within 1 megabyte. So that's something, if people want to try around with that, so that might be something you can even run on battery for a longer time. Yeah, that would be from my side. So I'm open for questions now. Go ahead. Yes. And then run the DHCP server or something to assign the address to the nodes for the So the addresses are actually coming from the layer 2 address of the hardware. So they are like the automatic address generation IP version 6. You could use DHCP on top of that if you want. I mean, that's really up to you. You have a normal IP version 6 link, but the generated address you get in the beginning, that is actually coming from the MAC address being auto-generated coming up here. So, but on top of that, you can use DHCP here. Go ahead, I see you.
I know usually the hardware transceiver is only one panel, but using the subscriber, would it be possible to configure several, not like you need to kill one layer, but like have several multiple panels?
Yeah, we actually haven't really thought about that much. I know that at least 1 or 2 transceivers that support. I know that there's at least 1 or 2 transceivers that actually support multiple PAN IDs. Yeah. On the kernel side, we haven't really looked into that. So that's something we might. Actually, I don't know right now if it would work or not, but I would suspect not at the moment. So that really you need to test it out and find out what is locking and what not. So I'm not against that. It's just something that we need to look into. Was that there? Yes. Yes, I never did that. There are different transceivers that are not 15.04 itself, but you can run the Mac over it. The problem is with something like the hardware accelerated features, like the sending out the acknowledgement frames and stuff like that. That is something we rely on the transceiver hardware on. So that if you ignore these parts, you can do that. I know that, for example, Riot or Contiki, I'm not sure, they also have support for some TI devices that are not 15.04 compliant itself, but just an RF transmitter, and they run 15.04 over it. So on the Linux side, we never did that because we really rely on some of the hardware features. You could try that out. I mean, in the end, for us, it just means having a transceiver driver, a hardware driver that brings the stuff in. So you can try that out if you want. But I never did. So over there.
Have you tested interoperability of your stack with USB-based border router things that popped up, for example,
most of these border router things that are just a small thing, they normally run something like Contiki, just a forked version of Contiki on it. I mean, there are different ones, I know that, but so that's something we test against. There are other border router things with OpenThread, for example, that's the same stuff. That's something we tested a little bit against. I mean, we can test against the whole thread stack because it's a lot more, but just the basic things to get frames and other systems. So that's what we did. We don't really have tested against all kind of hardware. So I think we're running out of time. Okay, yeah, so I'm around, so